All right, I'm going to begin anyway. So, um, first of all, as I mentioned during class, so we're going to have 3 questions in exam 2. So one question is going to be velocity, position, and acceleration analysis. I'm going to give you a 4-bar linkage, and you should be able to find all these 3 types of analysis. You need to find all the equations for all these 3 types of analysis. So the second question will be a 6-bar linkage, so which is going to be very similar to your lecture 7. And make sure you check those both examples in lecture 7 really carefully. And the last question would be a 4-bar linkage with a triangular or even a weird shape coupler. So that's why, first of all, I would like to go over your homework number 2. All right, so I mentioned multiple times during class. So when you see a very weird shape for your coupler, and then the point of interest is not, when your point of interest is not one of the joints, so you don't have to worry about that. So you first find all the joints. So you find where the basic 4-bar linkages are. And then if you find that 4-bar linkage, then you just first solve that 4-bar linkage. And then you use the position vector to find the position of P in the end. So that's something you already experience when you complete homework 3. But then I'm going to ask you to consider 2 special cases. So the first one is, what if I want to ask you, what's the velocity of point P? So that's actually homework 3. But then I haven't got a chance to post the solution yet. If you need to calculate the velocity for point P, so it's actually the same thing. You start from O to P, starting from the position vector, and then you calculate the time derivative for these position vector. Then you're gonna get position for P relative to the starting point O2. So relatively simple. So you have to go back to the very first lecture, the definition of velocity. So that's it. And the second special thing is, in this case, I'm giving you O2 as the origin of the global coordinate system. What if I give you a random point? For example, I name this point like O1, or name these points O3. I give you the coordinate for O3, like let's name it as X3, Y3 in the global coordinate system. Can you find the position vector O3P? So it's actually simple, right? You just first, in order to find your O3P, you need to go back to your origin first. So that's why your O3P vector equals to O3, O2, plus O2A plus AP. So just one more step. Perhaps I'm going to give you a new reference point. It's not the origin of the global coordinate system, but then you need to apply the basic idea we learned in lecture 1, which is how to find the right position vector. So you always start from the reference point, and then your destination should always be the point of interest. So no matter how long that path is, you just connect all the dots, and then you're going to find the final position vector. So just pay attention to the question. Read it carefully. So I might not give you the origin as a reference. Okay. Any questions? All right. So that's for triangular coupler. Let me see. The other one is actually for position analysis, velocity analysis, and acceleration analysis. So here is a very good example we used in both quiz 2 and quiz 3. So let's try to do these three types of analysis using this example. So first of all, you need to locate where your input is. So you know that, okay, in this case, your link number 2 is the input. We know is velocity. And then we also know this velocity is constant. When I say velocity is constant, that means theta 2 double dot, that's 0. So 0 angular acceleration. So theta 1, that's your ground link. In this case, your theta 1 is not flat, which is not 0. So the next step is you need to find all the unknowns. So theta 3, theta 4, these two orientations are the unknowns. So first of all, let's try to find the position analysis. To do position analysis, you need to find the vector loop. So when we need to find the vector loop, the first thing you need to find is the joints in the system. So you have O, A, B, C, these 4 joints. So connecting these joints together, you're going to find a complete loop. And then you can pick your favorite direction. In this case, I pick counterclockwise direction. So then that gives you the direction of each vector. And then you just write out OA plus AB plus BC plus CO. And then that goes back to 0, or it forms a 0 vector. So the next step is you need to describe each vector using the parameters presented in the figure. So your OA equals to, in this case, it starts from point O. So your O is the starting point, and then your angle theta 2 is defined around point O. So that's why everything is simple. You just directly use the theta 2. And then you have your AB vector, the same thing. This vector starts at point A. So your angle is defined at point A. So we can directly use the angle theta 3 over there. And then we have our BC. BC is kind of tricky. So your BC starts at point B, but then your angle theta 4 is defined around point C. As I said in class, we need to revert the direction of this vector such that your C becomes the starting point. But then the other thing is your theta 4 is not defined in the common way. The common angle we're seeing is actually something, the theta 5, right? So that's why your minus CB is negative R4 EJ theta 5. And then we need to do one more step, how to connect your theta 5 back to theta 4. But then we don't know theta 4, but then minus theta 4 is more familiar because then it becomes a counterclockwise direction rotation. So then due to the geometry constraint, your theta 5 plus minus theta 4, the sum of these two angles should give you your full pi, right? That forms this flat line. So that's why it becomes full pi. So you have minus R4 EJ theta 4 plus pi. You replace the theta 5 by pi plus theta 4. And then, as I said in class, when you rotate a vector by 180 degrees, you're just changing the sign of the complex number. So minus R4 becomes positive R4, and then EJ theta 4. All right. So then the last one is CO. Again, it starts as C, but then your angle theta 1 is defined around O. So it's better to revert it. And then we have minus R1 EJ theta 1. So we have 1, 2, 3, 4 vectors. And then we know the original equation. We just plug everything back in. Minus plus R4 EJ theta 4 minus R1 EJ theta 1 equal to 0. So that's the complex equation we find for position analysis. So, oops. So you can actually convert this complex equation decompose it into two real equations. And then these two real equations, one is along the real axis, the other one is along the imaginary axis. And then you can use Newton-Raphson to solve them all. So that's for position analysis. So the next step is, let's start from these position equations. How can we find velocity based on these position equation? So in class, what I did is you can define the first equation as F1, the second equation as F2. You just calculate dF1 dt equal to 0 and dF2 dt equal to 0. So these two equations should give you all the linear equations you need for velocity analysis. So I'm going to use dF1 dt for example. So you can do these dF2 dt after this virtual office hour. So dF1 dt. So we need to calculate time derivative for the first equation. The first thing you need to do is find all the time varying parameters. So theta2, okay, is rotating, so that's changing. R2, that's the constant length, is a constant. Theta3 is rotating, theta4 is rotating, and then R3, R4, they are fixed length because that's a fixed link. So R3, R4, they're constant. Theta1, that's the orientation of your ground. It's never moving, so that's a constant. R1 is also a constant. So you only have three time varying variables. So then you just need to calculate time derivatives with respect to these three angles. So don't worry, just calculate one by one. So the first one is cosine theta2. It becomes minus sine theta2 dot. The way we get from here is because we're using this equation, derivative of cosine theta dt equal to minus sine theta times theta dot. That's the relationship we need to use. And then R2, using that equation, you can just copy and paste and then find all the other derivatives. Because theta1 and R1, they're all constant. So the last term is actually constant. It's not changing with respect to time. So the time derivative is 0. So that's the first equation. You can actually do the same thing, calculate time derivative for the second one. And then in that case, you need to use this relationship. Time derivative for sine theta equals to cosine theta times theta dot. That's the relationship. And then you just need to copy and paste again. R2 plus cosine theta 3 dot R3 minus, plus cosine theta 4 dot R4. Again, your theta 1, theta R1, they're constants, so it becomes 0 after one time derivative. So usually in the exam, I'm going to ask you to convert these two linear equations into matrix format. So what you do is you first find all the unknowns and then collect them in a column vector. So theta 2 dot, that's something we know because that's the input of your system. So we don't know theta 3 dot, we don't know theta 4 dot, and then we need to find all the constant and put them on the right-hand side. And we need to find all the coefficients. And then usually the first row is for equation 1. The second row is for equation 2. So then right now the equation 1 becomes this equation. Equation 2 becomes this equation. All right. So let's find all the constants. So all the terms that has theta 2 in it, that's our constant. So because we move this term to the right-hand side, so negative becomes positive. That's sine theta 2. Oops. Theta 2 dot and R2. The same thing applies to the second equation. We find these constant term, kick it to the right-hand side, that becomes negative cosine theta 2 theta 2 dot R2. So that's the constant. And then we need to find the coefficient. So the first row indicates first equation. The first column indicates the first unknown. So first equation, coefficient for theta 3 dot. So that's it. So it's minus sine theta 3 R3. The second coefficient is first equation, coefficient for theta 4 dot. So go to first equation, coefficient for theta 4 dot, that's minus sine theta 4 R4. So you just repeat and find the coefficient for the other two. So that's cosine theta 3 R3, cosine theta 4 R4. Okay, that's how you convert two linear equations to matrix format. All right. So actually in class, I also give you a another method, which is J theta 3 dot theta 4 dot equal to C, right? So this J is your Jacobian matrix, and then C, we name it a constant matrix. So as you can see here, so these big matrix here, that's your Jacobian. And then this column vector here is your constant column vector. So the reason why I name it in this way is that's going to help you to do acceleration analysis. For example, what if we need to do acceleration analysis for this problem, then you don't have to calculate one more time derivative for these two equations again. You can directly start from these matrix format. So let's see what we can. Okay, so the theta 1 is gone. Is because theta 1 is a constant. So we if you go from we call it position equation. Yep. And then that's velocity. So from position to velocity, we calculate one more time derivative. So that's why all the time invariant terms, they're gone. Okay. All right. So let's calculate the acceleration. So the acceleration you can directly calculate from these. Let's see what's the best way to show it. All right, I'm gonna find it here. So in order to calculate acceleration, we need to find theta 3 double dot and theta 4 double dot. That's the only two unknowns we don't know. And then we name these as x double dot. And then you can also name the velocity column vector theta 3 dot and theta 4 dot as x single dot. So from these matrix equation, you have J times x dot equal to C. In order to get x double dot, we have to calculate time derivative on both sides, right? And then according to the relationship, you have J times x dot, that becomes J dot x dot plus J times x double dot. You have to calculate time derivatives by part, and then that equals to C dot. Okay, so then your equation should be Jx double dot equal to C dot minus J dot x dot. Up to this point, before we do acceleration analysis, we already know these velocities. We already know our Jacobian. We already know the constants. So that's why everything on the right-hand side is known. So then we can use, and then we can invert your J matrix and get x double dot. And then the next challenge is how to find C dot, how to find J dot. So your C dot, you need to go back to your C. So your C dot equals to time derivative of the first term, d sine theta 2 dot R2 dt. Oops. And then you calculate d minus cosine theta 2 dot R2 dt. So these expressions in the bracket is directly copied from your velocity analysis. Then you need to calculate these time derivatives. Let's see what that C dot is. So again, your C dot has two time varying variables multiplied together. You have theta 2 and theta 2 dot. So you have to calculate it by parts. You have first calculated for theta 2 dot. You have sine theta 2 dot becomes double dot, and then R2 is a constant. And then the second one is cosine theta 2 single dot square and R2. The first term is from time derivative of theta 2 dot. The second term is from time derivative of theta 2. And then you repeat the same thing. You have minus cosine theta 2 double dot R2 plus sine theta 2 dot square R2. It's just a lot of time derivatives, and then you have to be patient. So that's your theta dot. And then you can also find your J dot. So your J dot would be, your original J is here. Then your J dot is just time derivative for these all four entities. So sine theta 3, there is only one time varying component, which is theta 3. And then it becomes minus cosine theta 3 dot R3. And then minus cosine theta 4 dot R4. Usually you're going to see a lot of symmetry in your Jacobian. For example, in this case, the second entity is almost the same as the first one. It's just the subscription changes from 3 to 4. So that's why you don't have to calculate twice. Just copy and paste very carefully. Yes, correct. Because in this case, our theta 2 double dot is 0. That's a very special case, which means you have constant angular speed. But in the exam, you might see angular speed with certain acceleration or deceleration. So, yep, you cannot just directly put 0, but usually just the rule of thumb is try to keep the theta 2 double dot there. All right, so then we can do the same thing to calculate second row for your J single dot. Cosine theta 3 R3, that becomes minus sine theta 3 dot R3. Again, due to symmetry, so you just change this subscript. So you copy this term to the last term, and then change all the 3's to 4. You have minus sine theta 4 dot R4. So up to this point, you have a J dot, C dot, then you know your J dot, you know your C dot, and then your X dot is actually something you calculated from previous velocity analysis. So it's also known. So this coefficient is still J, is the same J here. So you know everything except for the acceleration. So you can use the MATLAB to solve for the acceleration. All right. So that's how you do system mechanism analysis. Always start from position. Once you know the position, then you can do one more time derivative, find velocity, and then you can do one more derivative, find acceleration. If you want, you can actually do infinite number of time derivatives, but then usually beyond acceleration, those variables have no physical meanings. So that's why we don't care about them. All right. So actually, this virtual office hour is pretty short. And do you have any questions? Right. In the exam, I would only ask you to provide me the equations, and then I won't ask you to solve those equations. For example, usually you're going to see nonlinear equations for position analysis. I might ask you, okay, what is the Jacobian you need to use for Newton-Raphson method? So for the other two, you're going to get like linear equations, but then just put them in matrix format. I'm not going to ask you to solve them. I'm not sure what you mean by general form. Oh yeah, exactly. Correct. So when I ask you to do velocity analysis, then you can assume that all your positions are already known. Yep. Exactly. So perhaps I won't give you a certain value for those lengths, but then you can assume those lengths are constants and already know. Okay. Cool. So exam 2 should be relatively easy. Just pay attention to these two quizzes and then try to double check your class notes and homeworks. They should be really, really similar. All right. Have a good weekend.